So there's a lot of different relations that you can build from a starting point. In other words, you have a couple of relations, you want to build new relations from them. Some of them are relations where you look at all of the paths of a certain length or just paths in general. We talked about those in class. You can also look at ones where you merge several different relations together. But here I wanted to go over 4 different types of relations that you can build from some given relations. So suppose you have 2 relations, R and S. Picked S here because we're dealing with 2 relations. Pick your favorite letter. And with the appropriate domain and range. Specifically, they need to be on the same building sets. So if A is a relation on A cross B, S needs to be a relation on the same A cross B. And that's the only thing you really have to have in terms of, well, that's not true in all things that you build, but in terms of the 4 things that I'm about to show you. Okay. So just to make our life a little bit easier, let's go ahead and pick an example here with respect to what relation R and S will be. Alright, so suppose we have these 2 relations. Our building sets A and B. A is going to be the integers 1 through 4, B the letters A through C, and both the relations R and S are going to go from A to B. So the first entry of the ordered pair will come from the integers 1 through 4, second entry from A through C. Relation R are those ordered pairs right there, those 8 ordered pairs, and relation S are those 4 ordered pairs given at the end there. Okay. Now, the first guy here on the list of 4 different operations we're going to do on these relations is going to be the complement of R. Now, the complement of R, when you deal with complements, you always have to know who the overarching universe is. When you're dealing with relations, the overarching universe is going to be your cross product. So here, your complement of R is literally going to be the cross product, whoever the subset of R is, and then you subtract out R. So in our particular case here, you look at all the ordered pairs that R didn't have. So here with R, we had the ordered pairs 1, and it could end with either A or B. So the missing one was 1C. Starting with a 2, we have 2B, 2C. So the missing one is 2A. Starting with a 3, we have 3A. So we're missing 3B and 3C. And starting with a 4, we have all of them, so we close off the curly braces, and that would be the complement of R. And that's literally it. There is no more. Okay. So complement. Now, with the -1 up there, this is the inverse of R. The inverse of R is where you swap your coordinates. So if you were thinking of these in terms of x, y coordinates, this is where you would swap the first and the second position. So same number of ordered pairs as R, we're just going to switch the order. So our first ordered pair was 1A, we'll switch it to A1. Second ordered pair was 1B, we'll switch it to B1. Next ordered pair was 2B, we'll switch it to B2. Then we had 2C, we'll switch it to C2. Then we had 3A, we'll switch it to A3. Then we had 4A, we'll switch it to A4. We then had 4B, we'll switch it to B4. And lastly, we had 4C, we'll switch it to C4. And that's literally all you do. Don't overthink it. Okay? Some people like to keep it in the exact same order like what I just did. Some people like to do one step further, and after they write it out in the exact same order, they then order it and put all the guys whose first position started with an A together like we normally would, then all the guys that started with B, then all the guys with a C, but that's personal preference. Now, the next operation is union. Don't overthink it. As long as your 2 relations are built from the same cross product of, in our case, A cross B here, you just union up the ordered pairs like you normally would back with sets. So we're just going to merge all of these ordered pairs. So if we look over here, actually we look to see what's common to both. So we definitely have everything that was in R. So we have 1A, we have 1B. Now R was missing 1C, but we have 1C over here in S, so I'm going to go ahead and add it in right here. Then if we start with a 2, R had 2B and 2C. S doesn't have any 2, so I'm just going to copy down the ordered pairs that start with a 2 from R. Then we look at the guys that start with a 3. We have 3A from R. S also has a 3. It has 3C, so we'll add in that extra 1. So those two are coming from S. Now 1B also came from S, but we already had it in R as well. And then we have the guys that start with 4. So we have 4A, 4B, and 4C. All of the possibilities that start with start with 4 are in relation R, so we've got all of these guys here. Now, technically speaking, we also have the one that was over an S, but it's a duplicate copy, so remember, don't write down duplicates. And that takes care of union. Last one here deals with intersection. So when you're dealing with intersection, you're looking at the ones in common to both. So notice that's no change whatsoever in dealing with sets versus now with relations. So notice there's only 4 objects or 4 elements over here in relation S. There's only 4 relations inside of relation S. So you just check to see which ones are common to both. So notice 1B is in both the 2 relations, so we'll write down 1B. 1C is not in R, so we won't write it down. 3C, not in R, so we won't write it down. 4A is in R, so we will write down 4A. And that's it in terms of unions. Now notice, everything we just did right here was with respect to sets. You can do all of the same stuff with both the matrices as well as the digraphs. Okay, so what happens if you were working in your digraph and you wanted to do this same sort of idea? Okay, so we're going to look at the same 4 relations or same 4 new relations we want to build, but now we're going to look on digraph. So I had to switch up the examples. Our building set here is now going to be 1, 2, 3, and we'll have the new ordered pairs. So first 2 relations are only going to deal with R, so let me go ahead and put R in its digraph form for us. So the first relation, our complement, is all of the relations in A cross A that are missing from R. Okay, so R is now, in terms of the arrows, what we see in that digraph over to the side. So if we go ahead and put the picture in the exact same orientation, specifically the vertices in the exact same orientation, notice, what do we have? 1 and 3 have loops on the original, so 2 does not, so that's the missing guy. 1 and 2 have both the 2 possible edges between them, so nothing new will go over here. Between 2 and 3, we have the edge 2, 2, 3, so we put in the one that was missing or not in the other picture. And there were no edges between 1 and 3, so the missing 2 guys are right between 1 and 3. And that's it in terms of the complement. In other words, any edge that could be added in but isn't in the original digraph, that goes in the complement. Now, for the inverse, the digraph associated with the inverse, remember what we did with the ordered pairs, you flip-flop the order of the ordered pairs. Well, if you flip-flop the order of the ordered pairs, that means you flip-flop the relation orientation. The relation orientation tells you where to stop and start your arrow. Well, not only that, it tells you which vertex you're starting and stopping your arrow on. So if you flip-flop that order, the arrow will still be in the same location, but the direction of the arrow will flip. So here, and we'll focus on the non-looped edges first, 2 to 3 will switch and flip-flop to 3 to 2. 1 to 2 will flip to be 2 to 1. 2 to 1 will flip to be 1 to 2. And notice in that case, it doesn't look like there's any difference. The loop 1 to 3, if you flip-flop 1, the loop at 1, if you flip-flop the order of 1 and 1 is still 1. And the loop at 3, if you flip-flop that one, is still 1 and 1. So notice the only change in this particular relation was just the 2 to 3 arrow flip-flopped its direction. Technically, everybody else flip-flopped their directions or reverse directions as well. It just was hard to see because of the type of edges they were. Now, with unions and intersections, you need to have at least 2 relations. So now we're going to be using both the relations R and S. So we've got the digraph of S prepped up here. It looks different. We haven't used that one yet. We've put in all of those 5 relations as the direct edges, and we're still using the same digraph from R that we were just using. Now, to create your union, or the digraph of the corresponding union of R and S, what you're going to do is you're just going to put in all of the arrows, all of the directed edges from both the 2 digraphs. don't duplicate anything. Just like with sets, you don't duplicate an object or an element. Here, we're not going to duplicate an arrow. So at 1, we've got the loop from the relation on R. We also have the 2 edges from 1 to 2. Notice I'm just going to copy down the relation here from R. Okay. Now if we go over to S, we'll add in any of the edges from relation S that are missing. 1 to 2, we already have. Loop at 2, we're missing, so we'll put it in. 2 to 3, we already have. Loop at 3, we already have. And edge from 1 to 3, we're missing, so that would then complete our union. Same deal with the intersection. The only difference here is you're only going to add now in the edges that are in both of the 2 digraphs. So notice here in our digraphs, we have the loop at 3 is in both of the 2 pictures. We also have the edge from 2 to 3 in both of our 2 digraphs, and we also have the edge from 1 to 2 in both of the 2 digraphs. So those will be the edges that we'll put in. So 1 to 2, 2 to 3, and the loop at 3. And notice if we go up here and double check to see if that works when we're looking at our ordered pairs. 1, 1, 1, 2, yep, that's the same. 2, 3, 2, 1. I wonder why we reverse those two. 3, 3, 3, 3 is here, and 3, 2, 3, 2. Okay? And those are the only ones that share or are in common to both of those 2 relations.